Okay, now let's get back to the talk. I decided to talk about ranges. Why? Well, I think ranges is one of the features that was in Boost, which is a library, a C++ library. Anyone who doesn't know it and who's programming C++, please look at Boost. And there's a Boost range library in there, and that library changed the way we program more than anything else we had anywhere in the library. So Boost range made a big difference. And then we started developing our own range library. And now we also got involved a little bit with C++ standardization. We are sitting on the C++ standardization committee. And there is going to be an upcoming standard in the C++ library for ranges. So there, we got involved a little bit in how do you design such a library. And I want to basically present to you, first of all, why ranges are good, and also many of these little nitty-gritty details of how you design a good range library. And while doing that, we will talk also about technical things inside C++. So now you've basically had all your hacking and assembly code and stuff like that, and now you're going to go to the completely opposite direction, and we're going to talk about the C++ as a language and pitfalls and idiosyncrasies that you'll find inside C++. Okay, before I start, I want to ask a few questions of where, basically, to gauge where you are in terms of C++. So, and another thing, please ask questions, okay? Ask questions during the talk, and if you want to discuss something, if you want to start an argument, all right, feel free to do so as well. I like arguing, not with my wife, but here about C++, that's all fine. All right, so first of all, the questions. Who has heard of argument-dependent lookup? Hands up. Okay, I'll explain it during the talk, but I guess not too many. Who knows what an R value is versus an L value? Okay, more of you. Good, good. Who knows what an int refref is? Okay, also quite a few. Okay. Who knows what int refref is? Okay, what is it? What is it? An int ref? Yep, it's an int ref. These are reference collapsing rules. So just to give you the resolution, R-value references, for those of you who don't know it, I won't discuss it in detail, but basically the idea is as follows. This is a new feature in C++ 11, and they try to solve an efficiency problem. They try to basically say you return a vector from somewhere, okay? Or you pass in a vector by value. Well, you say, oh, this is a bad idea, right? Don't do that. Right? Use references. Okay, but sometimes you have to do it. Now you have a vector by value, and you pass it into another vector by value. Usually the copy constructor would get invoked, right? Okay, that is very expensive. You have to copy the whole vector, and you have to allocate memory and all this kind of stuff. If you knew that you can throw away the vector, you don't need the vector anymore afterwards, that you are copying from, that would make the whole thing quite easy. You would basically empty the vector, and you would take all the resources and attach it to your own vector and say, oh, I just copied myself from this thing. I destroyed the other guy in the meantime, but if I knew that's okay, that's fine. This is what int refref is. So a vector refref acts like a reference, except that you know that you can demolish that vector. You can destroy that vector. Now, that's all there is to it, really. Otherwise, this thing is a reference. It is still a pointer to some vector. Underneath, if you look inside the assembly code, looks just like the same, just like a reference. It's all good. Now, the compiler will generate these, or will match these refrefs for you in some places. For example, there is now such a thing as a move constructor that has as a signature not the typical type const reference that you would find as in a copy constructor. Who's not familiar with a copy constructor? Oh, thank God. Okay, it doesn't have the t const reference, but it has a t refref as a signature. And now this knows, okay, if the compiler knows I can throw this thing afterwards away, I won't need it anymore, it will invoke the trefref constructor. And this is called the move constructor. This is a new thing in C++11. Now, when does the compiler know that? Well, for example, if you just return from a function that returned a vector by value, you just return the vector. Well, you know, I haven't assigned this vector to anything. It's there. It's a temporary value. You can the compiler will automatically match. If you then assign it to a vector, or you construct a vector from that return value, the compiler will match the trefref constructor. And then you can just take all the resources out of the vector and be really fast doing that. Okay, so that's the int_refref. Now, int_ref_refref is important for perfect forwarding. Who doesn't know perfect forwarding? Okay, now perfect forwarding, I think there is going to be examples for perfect forwarding. The idea is whenever you're getting something, you want to pass it on as you got it. A constref stays a constref. A ref, an L value reference, a regular reference, single ampersand, will stay in a single ampersand. And an R value reference will stay in R value reference. So whatever you're getting, you're just passing on. And that's something that people wanted to do a long time, and it was always a bit tricky in the old standard because you needed basically two overloads. You needed a constref overload and a reference overload. The problem is, what did you do if you had 10 parameters? Well, you needed 10,024 overloads because you always had to have a reference and a constref for every single argument. You need all combinations, and people couldn't do it. Okay, so now it's not a problem because essentially you are writing into your template parameter list, instead of t constref, you're writing t refref. And this is where all these things come in, because now if you have a t here, t refref, this is a t, okay? If you put an int ref as the t, you just matched int ref. And this is kind of the trick they did. They said, okay, if you're writing trefref into your parameter list and you're passing in a regular reference, I can make t a regular reference. So if I plug this into my template, I have a t and a refref. Then I have t constref or t refref. And it happens beautifully to collapse to int ref. So I actually passed int ref to the function. This is all there is to perfect forwarding. Now, maybe we will encounter it as in the talk, and then I'll point it out to you again. So let's get to Ray. Yes.
Just maybe a slight addition to the explanation. I guess it's worth pointing out that the same syntax, namely two ampersands, has two different meanings. Because it's at one point referring to an R value reference, but when you do perfect forwarding, it's the same syntax, but it's actually this, some people call it universal reference.
Yes and no.
Okay.
Not really.
Okay,
it doesn't really refer to something else. The reason is the reference collapsing rule. Okay? So if you imagine this is a T, and yes, universal reference is a term that is important. That's basically whenever you have a refref with in front of it a free template parameter, template type name t refref. That's a universal reference. In the language, it's all consistent. This is not a special case, really, because you can make the t a int ref, and then if you plug that into the t, you say the t is now int ref, then in my function declaration it says int ref refref, because before it said t refref. And now I have t made t int ref, so you have int ref refref. And now they made up rules and said, if you're writing this, int ref refref, this actually collapses to this. And so you get t to be int ref, and it's all good again. Okay? So I'm just saying that because there's nothing magic there, really. So if you write this into a variable, if you just write a variable, declare a variable like this, it will also work. You can write int ref refref a, and a is going to be of type int ref. Okay? And there are just these collapsing rules everywhere in the language. C++ has these collapsing rules per se. So I think, so int ref is int ref. Okay? So these collapsing rules are at work in other parts of the language as well. They're not so special to R-value references. Okay?
And the term is not universal reference anymore. It's now called forwarding reference.
All right. So let's call it forwarding reference. He was just at the standard committee meeting, so he knows. Okay, now let's talk about ranges. Why ranges? I said that they changed actually the way we program. And here you can see why. Okay? So usually, if you are in the regular standard library land, then you can have a vector like this, and you can sort it, and you say, if I want to sort, then I have to say, oh, I have to pass two iterators, vec begin, vec end. So now it's sorted, fine. Now you say, I want to make it unique, okay, and I will throw away double values, which I can do because it's sorted. So I have vec begin, vec end again. And then I have to erase, and I again say vec.erase, la 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 la, vec end. So I erase from this iterator to that iterator. Now, we wrote vec really, really often, and it gets really, really ugly, right? So what do we want to do? Well, the pairs of iterators are really one thing. We are talking about a range of values. And it would make sense to actually put these two iterators into a single object. And that's the basic idea of ranges. So pairs of iterators, they belong together, we put them together. And then you can write something like this, which is much nicer. You say, I sort the vector, then I unique the vector, and it returns an iterator. Well, unless I have this special parameter here that says, I don't want your iterator. I don't want the range that comes after your iterator. Iterator to the end of the input range. So you could write something like this, and then you say, oh, I want to throw this away, range erase. And then you have what you actually want. Now, this you can't write yet, but this is something I would like to write. Like to be able to write. And we will do this frequently in the talk when we first say, this is how I want to write it. Why can't I write it that way? Well, we have to make the world so that you can write it that way. So this is a good design, a good library design. And there was a question somewhere.
So this line means that we leave only copies in the vector? Or?
Okay, what does it mean? Let's say, and this is something that I'll discuss below, but then if you're asking, I'm discussing it now. What does this line really do? Often people say, I have a bag of values, and I would like to put them into a data structure, and then then I would like later on, after I put all these values into a bag of data, this bag of values into a data structure, I would then like to do queries, like, do I have this value in my bag? Yes or no? Or which value do I have associated with that value? Traditionally, you would do that with a map, right? You just say, okay, dump all the values all in a map, map, you m place back, or m place, and then later on, you do queries on the map. This is a terrible idea. This is okay if you do mixed insertions and queries, and insertions and queries, and insertions and queries. Then do it that way. But if you first have all your insertions, and then you have all your queries, don't do it that way. Maps are red-black trees. They're eating up. Every node, every value that you put into a map is a separate piece of memory. And they contain pointers that point them to all the neighboring nodes in the tree. So this is a bad idea. This is the right way to do it. You dump your values into a vector. Then you sort the vector. Then you throw away with std unique all the duplicate values. Then you have every element is only in there once. And then after you did that, you erase with the unique. What unique does is it throws away all the values, but it doesn't compact the vector. The vector still has kind of garbage at the end that you then with erase, you just throw away. And then you have a vector that has all the values in there only once, and you can do very efficient lookups on that vector. This is much more efficient than using a map. So this is a very frequent complaint when I do a code review. It's like, oh, why did you use a map again? So don't do that. Still, there is I could claim there's a bug in this algorithm. And I want to ask you, what's the bug? I think you understand what it does. It sorts, it throws away the duplicates, and it erases all the garbage at the end. So it's really not that difficult, really. But there's some bug in there. I think you had your hands up first.
Yeah, I'm not sure anymore if it's really the thing, but I just wondered, so when I call erase, I must be sure that the two iterators I pass in make up a valid range.
Yes.
And maybe there's a case where the return value of standard unique wouldn't be, where this would be equal to the end of the vector, and then I wouldn't have a valid range anymore.
You get
Something
end.
like this, but yeah.
It's all good. End is fine. If you erase end, he says, yep, it's good. You were next.
I see missing braces behind begin. Back begin.
Yes. Yep, that was one bug. That was one bug. Very good. Okay, next one. There's another bug. Go ahead. The same. Okay. No, there's another bug. And it will introduce you to this kind of very strict notion of correctness that I like. Okay? What does sort do?
Usually quick sort on the range. You get a quick sort.
How? What is it comparing?
The values
How does it compare the values?
with the smaller.
With the less operator. Correct. What does unique do?
It compares using the equal.
Yes, it compares using the equal operator. We are using the two different comparators for the sorting and for the unique. This is not guaranteed to work. Okay? This is not guaranteed to work. You may actually, if you have inconsistent equality and less operators, which may be a bad idea, but I mean, this is type T, right? You don't know anything about this thing, right? So you should be consistent. If you're using the less for the sorting, you should use the less for your unique. And, oh yeah, here it is, right? You just turn around the less, and you get your predicate for your unique operation, okay? This is out of practice. We had this problem, okay? So it's better if you use this very often, which you are bound to do because you're no longer using maps, you're going to write yourself a function for this. Okay, and I already told you, don't overuse set map. Okay, now we know why we want to use ranges. Now there are already ranges in C++ 11. There are range-based for loops. Who knows about range-based for loops? There are surprisingly many, right? So this is actually a feature in C++ 11. You can now say for int ref I, which basically means, okay, when you're getting your I out of the range, don't copy it, just give me a reference to it. And then you have, after the colon, you have a range expression. Now the range expression can be, according to the standard, an array, or you can have, it can be a class that has members begin end. They return iterators, which is like your plain vanilla vector, say, so that's fine. Or it has ADL, argument-dependent lookup, accessible free functions begin end. Okay, what's that? Before we get to it, because this is quite important because this is basically the kind of range support that's already standardized. We can't throw away old standards. It's impossible. Once something is standardized, it's set in stone. So if you raise your hand and say, oh, we should change the standard, everyone goes, wow, you want to change the standard? But there's gazillions lines of code, and they all use that feature. And it's impossible to change anything that's in the standard. Okay? So that's why it's now said and done. There must be ADL accessible free functions begin end. Before I go through what exactly that means, there's an interesting fact. Begin end is the other part that is kind of rangy in the current C++ library. And it also takes such a range expression, which can be an array, or it can have members begin end. So you can now write std begin of vector, which is the same as vector.begin. And they forgot ADL. Sorry. Yeah, we forgot. So that's kind of a shame. And we will fix it. But first, I have to explain to you what argument-dependent lookup is. And this is something that if you have never heard of it, and you program C++ for quite a while, this may be somewhat surprising that this exists. It has always existed, since even in the old standard, and it mainly causes bugs or unexplainable compiler errors for those people who are not familiar with it. So I want to explain how it works. If you have C++, look for a function overload, like func of x. If this thing is qualified, if there is a namespace in front of it, like std begin, for example, this is called a fully qualified name. It has a namespace. And this will only look into the specified namespace. So you will have, who doesn't know what a namespace is? Okay. So if you have a namespace in front of it, it will only look into this namespace. So it's all good, relatively easy to understand. If you have an unqualified name that doesn't have any colon something in front of it, or something colon in front of it, it will look into the current namespace, not surprisingly, all the parent namespaces. So if you nested that namespace into another namespace, it'll go all the way up to the global namespace. All these will also be considered. And it will use ADL. And I come to that in a second. One thing is important. It will first collect all the candidates for begin, collect all of them, puts them all on a big list, and then checks if there are any overloads that match your parameters. So it's very easy to get an ambiguity, because it's not like, oh, if it's in the current namespace, then I stop searching. It's first you collect all of them, and then you pick. This causes ambiguities, and that causes the funny compiler errors, because if this thing that you found is found using ADL, and you don't know ADL, you don't know how the hell did he find this stupid function? Okay? Now, and here's what ADL does. It looks at the function parameter types of your function. It looks at the parameters that you supplied. And it will actually look into its namespaces. So if you say func x, and x is defined is a variable, and it's defined in some namespace, it will look into this namespace and include all the funcs it finds there. Most of the time, there is none, and then you got lucky. Or it doesn't match. It's also okay. There's just no func that actually takes an x. But with all these templates flying around that have very, very littly constrained parameters, you have like a template type t, well, it could be anything, with just t ref in your parameter list, there are functions that match a lot of things. And then you are getting into trouble, because if the function parameter, if the namespace in which the function parameters live also define some begin, then you're actually going to find this begin. Now, why did they do that? Well, it's a little bit explained through the std begin. The std begin, or the begin, that is invoked when you're using the range-based for loop. Essentially, the idea was, say you have some library that has an existing data structure, and you want to make it rangy. Then you can now put into the same namespace where you defined the data structure, without touching the data structure itself, you can put in something like a free function begin of that type. And it will actually find this thing, because it's in the namespace. It's in the same namespace as your original structure. The problem a little bit is the ADL makes this very strong assumption that everything that you put into the same namespace kind of belongs together and likes each other very much. And that's usually the way people often use namespace, is not the case. And then you're running into trouble. Okay, but it goes further. Function parameter types. Then, if applicable, the template parameter types these function parameter types are instantiated with plus all the base classes of the function parameter types. Whoa, let's look at an example. So here's an example. You have a namespace ns, that was namespace. Now you have inside the namespace, you have structure t, and you have a function that just takes an unconstrained template parameter, a const ref, whatever. Okay, now you have namespace other, some completely other namespace. It doesn't have, it's not parent of ns or ns no parent of other or whatever. It's just two different namespaces that don't overlap in any way. And let's say in that namespace other you have a template defined that takes some freely defined type name p, whatever. Is somehow parameterized, that template. And it also doesn't have any relationship with the namespace. Now let's see what actually gets found if we have a function inside other. So first of all, you have structure derived here, where a structure that's derived of the type that's defined inside the namespace up here. Okay, so here it is accessing the other namespace, and it's grabbing that t out of that namespace. And you are calling func derived. Func is found in the other namespace. Now, the other case, if you have the temple that's defined up here, a structure that lives in our namespace, all fine, but it is parameterized with a type that's coming out of this other namespace. Now, this function will also be found. Then the func will also be found if you use this as a parameter. Because they say, oh, okay, temple is actually parameterized with a type that's coming out of the other namespace. Now, the madness has limits. If you have a derived from the template, so you have a structure that is derived from this thing, and then you try to call func, it does not compile. It won't find it. So this is, in a nutshell, argument-dependent lookup. Now, one very important thing, in particular if you are developing a library, is how do you avoid unexpected argument-dependent lookup? How do you prevent your library from not working in very peculiar circumstances because you actually invoked ADL? And it's a bit tough to kind of like think about minute details. You want to just do something that you rubber stamp in your code, and it's like, oh, I disable ADL. I disable ADL. There's no ADL here. Okay? And the very simple way to do that is to say, well, if in the namespace of my structure there is no other function defined, you're safe. Nothing can go wrong. And this is what exactly we are doing here. So we say, okay, ADL barrier, we put the structure T into the ADL barrier, and then we do a using namespace. We import all the names into the NS namespace. And this will actually not invoke ADL anymore. So that way, you are getting a T that lives inside NS, and you get a func that lives inside NS, but still, the T and the func won't see each other in the ADL way. And then you are safe. So as an effect, none of that compiles anymore. Okay? So think about that when you're actually doing library development, that you can prevent, or you should prevent, actually, ADL. Okay, now we would like to add the ADL lookup to begin end. And we will kind of develop the range library from here, right? So we kind of like say, okay, what do we have to do next? Well, stip begin is kind of broken. You would always have to write using stip begin and then begin, because if I'm writing stip begin, I just disabled ADL. So you have to say, okay, I want stip begin for my arrays and also for the classes which have members, but I would also like the ADL begin end free functions. So then I have to kind of write every time using stip begin and begin, which is kind of cumbersome to write. And really, you would like to have a range begin that you always use just everywhere in your code that automatically does the ADL lookup for you. Okay, here is a possible implementation. And to do that, I will talk a little bit about automatic return type deduction. Because what we're actually going to do is, down here is our implementation of begin. It lives inside the namespace range. Okay? Now I could say, hey, it's easy, right? I do namespace range, and then here I have my begin, and in there I'm just writing using begin, using std begin. Well, that doesn't work because the begin here would be called recursively, and this thing would never end. All right, so that doesn't work. We need to kind of escape into another namespace. So there is a begin impl that does exactly that. It just says it's using std begin, and here it just invokes begin without any in an unqualified way, without any namespace in front of it, and that will actually invoke ADL. And for ADL, it doesn't matter in which namespace I am, and the std begin I just pulled in explicitly, so it's going to be all okay. It does exactly what I want to do. Here is perfect forwarding. Okay, you see how it's written: template, type name, range, and then range, ref, range. And that basically means a constant reference stays a constant reference, a reference stays a reference, an R-value reference, one of these things that you can throw away, they still R-value references. A constant R-value reference, which exists, will also stay a constant R-value reference. There are constant R-value references. They're not particularly useful, but they exist. In order to basically unfold this thing into the original reference, you have to pass it to std forward range. What will this thing do? Well, it will static cast this thing into range ref. So basically, it just replicates, this std forward just replicates the type up here that you're getting and just passes it on as it is. So that's kind of the mechanism. You can understand it once and then just rubber stamp it in your program. This is perfect forwarding. Okay. Now, I want to talk about something else, which is the return decal type. I kind of got, when writing libraries, you are often kind of just forwarding things around. And it's nice if you don't have to think about too much about the return values. You kind of want the system to figure it out by yourself, because sometimes you just don't know the return value. It has also been, in C++ 0.3, people often had like these traits like iterator traits, difference type, iterator traits reference, iterator traits value type, whatever. This has gone a bit out of fashion because we now have decal type here to actually figure out the type yourself. So often you don't really quite know what the return type is, and you kind of want just to say, oh, just pretend I'm not there. Just like here I did the perfect forwarding. Now pretend I'm not there and just return. It's okay. Just take whatever this returns, and I want to return the same thing. Well, it turns out, and I want to talk a little bit about it because this shines a bit of a light on how decal type works, which is one of the more important features I think that C++ 11 has, figuring out a type of an expression or a variable. And this sheds a light on how complex that subject is. I don't want to go through with you through the mechanics of this return decal type. So, but we have implemented now begin. You can implement end exactly the same way. So that first little bit of our library is done. Now let's talk, as I said, a little bit about return type deduction in C++ 11. We do have it already, kind of built into your language. If you have a lambda like this one, it will actually figure out the return type itself. And you may have used it. I don't know if you've thought about the return type deduction much. But what's the type that is returned from this lambda? I already wrote it down there. It's always a value. They are kind of wiggling around the problem. They said, they understand, I mean, they're writing the standard, they understand exactly the intricacies that you will learn now too, but they kind of said, okay, the only way to do something default that is safe is it's always a value. It's not exactly a value, it's called a decayed value. There is a type trait, std decay, in C++ 11, and it will do things like turning arrays into the pointers to the first element. It also throws away references because you have to make it a value type. You have to make it a value. It will throw away all the references, R-value references, reference, whatever. It doesn't matter. It gets all thrown away. It will do more than that. It will turn arrays, for example, into the pointers of the first element. What it will do is exactly the same as if you are defining a template with template parameter t, without any reference after it, tt. This is by value, as you may know. So the t will get matched a value. Well, what type does t get if I'm passing anything to a function that is template type name tt? Well, the decayed value of your expression. This is exactly what will be used. And they did that, and this is actually the same rule that's actually used for the lambdas. And they could do that because they knew already that we have been doing this forever. We can easily put this into the standard because that type deduction that's happening, we've been doing in other places as well. Whenever we are passing something to a function that takes a t, an open, an unconstrained template of value type, we've been doing this type deduction all the time. So that's why we can actually, that's why they did it that way. Now, I want to go further and say, how can we do any better? But first, let's talk about the lovely decal type. If you think you knew C++, well, I didn't know it until 2 days ago. This is how decal type works. And maybe it's a bit tedious, but we'll see. Now, what cases are there? So let's say we have defined these variables up here. A value type, a reference, an L value reference, and an R value reference. And we say decal type V, decal type R, decal type RR. What this will spit out is what you may expect. It will replicate the variable types. But not if you put extra parentheses around it. The reason is as follows. If you are putting no parentheses around it, it will actually get you the type of that the variable is declared with. This is up here. Now, when you are actually using that variable in the program, it doesn't really have the type value int. Because you can do things like v equals 3. You can assign something to the v. Well, if v would be kind of act as a value, well, that would be like 3 equal 3. Well, that doesn't work, right? So this will work if the v is an L value, basically a reference. It acts like a reference. And this is what happens when you are putting these parentheses around it. It just makes that thing as, no, this is no longer a variable. This is what that expression, the role of that expression in the program. And that is int ref all the time, even with an int ref. And I think I have an example here for that. Let's see. I have an example here for it? Maybe I don't. So if you have a variable declared as int ref, and you pass it to a function that takes int ref, will this work? No. It's very strange. The reason is that they said, say you have a function that takes an int ref, or a vector ref, for better illustration. And I am accessing this vector ref. Then if I would pass it to a function that takes a vector ref, what happens to my vector that's behind this reference? Well, I passed it to a function that takes a ref. This function was free to throw away the content of the vector. It was free to destroy the content of the vector because it takes a vector ref. It basically assumes, hey, this is something I can throw away. And so when they designed the language, they said, well, this is pretty unsafe because maybe someone takes a vector ref on top and then uses it once and uses it twice and uses it 3 times. And the first guy throws it away, and the second guy doesn't have anything anymore because it's already thrown away, and the third guy doesn't have anything anymore either. So that is a bad idea. That's why they said whenever you are using such an ref as in a simple expression, it has L value reference character. It just acts as a regular reference. You have to pipe it through the std move to turn it again into an R value. And the std move kind of marks, it doesn't do anything magic. It does a static cast from the reference type to a ref type. It's just for you to mark, hey, oh, this gets now moved out of this thing, potentially. Nothing really happened yet, but with the std move, I gave the permission that something will actually happen when I pass this expression to a function that takes a std ref. Okay? And that's why the Deckel type of all these expressions is int ref. Now, it's different for functions. Functions, when they're returning actually a value, they are, again, just expressed as a value, as the return value. The Deckel type of that expression will actually be directly reflected in the Deckel type. And there, it doesn't matter whether you write single parentheses or double parentheses. And I forgot something, which is, of course, you have to pass in something to this function. So you have to, let's move this, and here you would have to put. Okay? So if you are invoking this function and you are checking basically what's the type that is coming out of this function, it doesn't matter how many parentheses you put around, you just get reflected the return value of these functions. Okay, so let's try to write a return Deckel type that returns what you pass in. Let's look at this. Now you can already see from what you know that this is bad. Why? What's the return value of maccessor? Huh? A value, yes, int, right? Because it's just a single parentheses around this thing, Deckel type of VA args here, right? So it will just take the value and it's int. That's bad. That's not how you want an accessor to behave. You want to use the accessor instead of the original variable. So you want to just be able to call the accessor and assign something to it, for example. It should be just like the original variable. So this implementation of return Deckel type doesn't seem to do it. Well, no problem, right? We just put double parentheses around it, around the Deckel type. And now it's all great, right? The accessor will return int ref. Because, as we said, when you put double parentheses, any variable will be int ref. So it's all good. How about this? Passing an a by value. A return Deckel type a.m. What would this be now? Huh? Again. Say again?
Undefined behavior.
Yes, undefined behavior. Why? You're returning a reference to a temporary or to a local variable, right? Bad idea, right? So this return Deckel type doesn't do it either. It's like, okay, how can we do this? Now, what's the cause of the problem? The cause of the problem really is that once this a was defined outside here, and it didn't die when the function returns, and in the other case, the a was defined inside the function, or as a parameter, it doesn't matter. It dies when the function returns. And there's no real way we can find out what the variable lifetime is of the thing that you're returning. So let's be a bit more careful, okay? Let's say we now have a safer return type for expressions. We just say, for expressions, we are trying to do one thing, and for variables, which seem to be tricky, we try to do something else. Now, this here is only gibberish, right? It just passes the Deckel type parentheses once and the Deckel type parentheses 2 times to this actual type function. And the type function does as follows. It says, if these two things are the same, we have a pretty good chance, it's not 100% because int ref will still match to int ref, but we have a pretty good chance that this is actually an expression. If it's not the same, they're trying to call us on a variable. And variables are tricky because we don't know the lifetime of variables. And so we say, hey, don't do that, okay? Now, what do we then return? We say, okay, if your expression, and we are now talking only about expressions, if the expression is a reference, then we actually return the expression, the reference. And otherwise, we decay the return value. Okay? We didn't have this in the original implementation that I just showed you, but I said, well, that is kind of the convention. Whenever you're returning something, you decay your expression. This is what the Lambda is doing, so we need to do this as well to be consistent with the rest of the world. And now, for variables, we do something that is a bit safer. We just say, okay, if we're detecting that we are returning a variable, then we try to avoid using this expression up there with this static assert. And now the user can decide. Either he can say, return me by value, because I'm a local variable, or return the variable by ref. Now, this return doesn't really mention variable, because if you want to return by value, it's always safe. It's always OK. Just do it. And here is you return the variable by ref. Okay? This is basically what the old thing did. But you have to be explicit. It's like, I know it's a variable, and I really want to return it by reference. And here is, as we saw, the variables are always L-value references. If there are values for the expression type is always L-value reference. So if you get anything else that's suspicious, and we static assert, it's like, no, you're using it for me for something that you are not supposed to use me for. Okay. Again, here is my ref example. As we already discussed, this is what I wanted to show you. This doesn't work, right? You have an int n, you have an int ref n, that you just moved the n into, so you created a r-value reference and to this n, and then you pass it here. This is still an L-value reference, so it's all good. This doesn't match, does not compile. And we discussed it already. Okay, is it okay now, what we did? Hopefully, right? Must be the end at some point. Can't be that difficult. Unfortunately, we have this. And here we are creating an R-value reference. Basically say, hey, move out of this a.m, which is, if you want to do that, is kind of okay because, yeah, you have something local, and you try to kind of move out of it and say, hey, scavenge this thing. It's going to go out of scope anyway, our A. So I would like to move it out, right? And then I put in my return decal type so that everything is safe. Well, this is an expression because it's a return value of std move. It's no longer a variable. But it's an R-value reference. And the problem is you don't know with the R-value reference whether the R-value that you are getting here out of the std move is actually referring to something that will go away now or that will go away later on. You already got the R-value reference from somewhere else. You just know I got an R-value reference. So we have to say, hey, R-value references, if you want to return them, that's not safe either. That's not a good idea either. And so we do it even safer. Oh my God. Again, this is just the regular gibberish, right? It just passes this stuff on to a return type deduction function. And it says, OK, first of all, variable and expression for an expression must be the same. Don't use decal type for variables, OK. But also don't use it for R-value references. And then you kind of do the same thing that you did before. If it's a reference, you pass out the reference. Otherwise, you decay the return type. OK? And then you need more options for the user. You need to say, hey, the return type, decal type, either you want the R value by value returned. This is this. You say, if it's an L value reference, then I return it. Otherwise, I decay it. I decay R values, so they're going to be returned by value. Or I do the other thing. If I know that my R value is actually pointing to something that I already got in, for example, by perfect forwarding, you may get in an R value, you may then get out an R value, but if you don't create any temporaries inside your function, you're actually safe to return by R value reference. And that's the second option that you have down here. And there is a question.
Yeah, why do you exactly use multiple arguments for your return macro? I mean, there's only one return type, isn't it?
Right. The reason I do that is, first of all, I wanted to keep you from reading all this stuff. Because this is always the same. I kept this always the same. Here's where the gist is going on. The other reason is that this decal type often gives a different value than this decal type, or a different type than this decal type. Okay? This is the expression decal type I put in here into the expression. This is the variable decal type that I put into variable. Okay? And if VARgs happens to be an expression, some function call, they're going to be the same. It's okay. If it happens to be a variable, then they are going to be the same only if that variable is an L-value reference. If it's an R-value reference, or if it's a value, most of the time, hopefully it's going to be a value, then you will get something else, and then I can scream at you. Okay? So that's why I'm always passing in both, so I can write these static asserts here. Okay, here's the overview. Yes? Yeah, more.
Yeah. Actually, that was not exactly.
Okay, go ahead.
Sorry,
Okay, maybe I'll tell you.
Why do you need to use v-args? I mean, there is only one arg, isn't it? I mean.
Very good. Very good question. Sorry, I already.
Yeah,
does anyone know why I did it? Yes.
To avoid that the preprocessor picks the first part of a function called the comma.
Yes. Right? I got into the habit, whenever I'm taking the first parameter, and only having a single parameter in my macros, always use VARgs. Because, I mean, if someone puts a comma in there, you probably just transport that comma into your expansion that you have inside the function. It can't be wrong. You're expecting only a single parameter. Why shouldn't someone be able to just put a comma in there? And otherwise, you always have trouble with comma. You have to put extra parentheses or whatever. If you just use VARgs, you can just use commas in your expression with which you call the macro, and will just expand it correctly. The world's nice, right? Doesn't work for 2 parameters, but actually almost. Because if you know that only the second part of your parameter, or the second parameter of your parameter list is such a thing that has commas, you can write something like, this is the macro here can look like x comma ... And then you can have the VARgs for the second part. And then some people can put in commas and everything, and it's all good. And as long as your first part is without commas, you are okay. If you need commas in your first part, there is boost pp comma. Look at it, then you can put in commas into your macros. Yes, this is a talk about C++. I'm sorry. I mean, this is, yeah, it's a mess. Right, yeah, it's a mess. It is. Right. Okay, so here is the overview. Okay, so return decal type, variables do not compile, L-value expressions is becoming tref, PR value expressions, values, PR values for, who knows what a PR value is? Okay, read the standard. No, it's basically a function that returning a value. It's kind of like an R, it is an R value, but as opposed, there are basically 2 different types of R values now in the standard. There is the R value reference that is pointing to an R value, a PR value, and there are these actual PR values, these things where functions return something by value. You have to imagine, like, when a function returns something by value, he basically drops its return value somewhere into memory. Okay? And this place in memory is the PR value. Now, if there's an R value reference, it's actually pointing to this PR value. Okay? And that is an X value. It's an expiring value. Wow, this is a PR value. And X values and L values together are GL values. Didn't invent it. Okay. So return by value returns everything by value. It's all fine, right? It's always, if I write T, I really mean decayed T. Variable by ref returns the value, the variable, as a tref. Because, well, it is nothing else. Even a tref is a tref. Return decal type R value by ref means it is for expressions, right? And it will return everything, all the expressions as they are, while return R value by value will turn this X value, or the ref into a T ref. Okay? So this is a little overview. And I don't know, I can give you the text if you like. We do use these things because you don't like to write in the decal type. You don't like to repeat yourself and write the whole thing again that you want to calculate the decal type off. So it's kind of handy to have these kind of macros. And yeah, it's ugly. So macros are ugly, but for certain functionality, there is little other option. Where's my mouse cursor? Oh, did my mouse just? No, there we go. Okay, let's return to ranges. We really wanted to talk about ranges. Here is the range concept for iterator pairs. This solves our original problem. We have two iterators, and we now want to plug it into the range-based for loop, for example. Well, it's actually quite easy. You just have it begin and it end, and begin passes out at begin, and end passes out at end. Or it could be easier. And now you can actually put this thing into your range-based for loop, initialize it with the curly brackets, with your begin and end iterator, and you can use your range-based for loop for something that actually used to be iterator. So if you have two iterators, you can adapt it to the range-based for loop. Okay, once we can do this, now we go the other way around. Now we basically adapted the iterators to the range-based for loop, and now we have to bring the iterator world into the range world. That means the range support in algorithm. You want to write some find that takes a range expression and finds the x. Now, how does that find look like? Here's a first shot. Okay. Now, return deckel type to rescue. You take the range, you take what you want to find, and you take the range const reference, what const reference. You say, well, what should I do here? Well, let's pick range const reference because really, I mean, I don't want to modify the range, right? So then that makes sense to just use range const reference. And then we're going to pass it on to std find, range begin, range end, range what? Does anyone spot the problem? Well, let's carry on. Now let's see. Sometimes the range that you pass in is going to be something like a vector. You have a vector, 3, 5, 4, and you call range find v, 5, which gives you an iterator to this thing. And you want to assign 6 to it. You want to replace this with 6. All right, that's what that is. That does not compile. Why doesn't it compile? Well, we took the v by const reference. And when we see up here, if we have a const object, it will only return us a const iterator. And we will pass that iterator out of the find. And we call star and const iterator and assign something to the const iterator. Well, const iterator is a const, right? You have a problem. So range find must return the strongest iterator there is. Now, there is a current consensus that the same should hold for R values. So this will basically do a find if on the int vector that you passed in, and it will int I equals star range find if, and it will look up the whatever returns int vector returns, it will do a find of that and return the iterator. And then you kind of plug the value out of it, which would be here, the first even value, and assign it to I. Now, this should work, surely. The current consensus is that the iterator that should come out of find if should actually be a mutable iterator. This is a little bit, you could say yeah, you could say no. I couldn't come up with a really good example where you would need a mutable iterator. In this case, you don't. In this case, you are just fine with a constant iterator. Still, what I showed you in the very beginning was kind of that we want to chain these algorithms. We want to say, do something with this algorithm, and then do this, and then do this, and then do that. And often these things are R values that you're passing in because you're getting it as a return value from some other function, and you pass it through the whole chain of algorithms. And in that case, it may be useful at an intermediate step to actually have a mutable iterator. If you want to sort this thing, for example, right? You need mutable iterators. So the current consensus is return the strongest iterator. Even from R values, not const R values, from R values, you're getting mutable iterators back. How do you implement that? This is how it works. You basically change the range ref here into a, you make this into a universal reference, or whatever, forwarding reference. Now, inside this function, this range ref, if called with a R value, is going to be, as we saw, an L value. right? So range begin, range end is just going to return mutable iterators, and std find will get mutable iterators, and thus std find will return mutable iterators, and the world is good. Okay. Now we saw that there is a problem with the constantness of ranges. We will come to an exercise, no worries. Does this compile? So we say, oh yeah, this is all off, and the range, const reference range, so we don't want to modify the range. And actually, we would like to keep our promise. We would like to say, no, range begin range, true. Well, that's not what all is supposed to do. All is try to find out whether there is anything true inside this range. But, well, does this may still compile? Unfortunately, yes. Because if we have iterator range, remember how it was implemented. Oh, here I have it, practically. This it here may be a mutable iterator. So if I pull this out, doesn't matter whether it's const or not, I'm getting that iterator back. And we only have that iterator. It's always a mutable iterator. It doesn't matter whether this object is const or not. I'm getting this iterator back, and thus I can assign to this iterator. This is ugly. So really the constantness depends on the IT that I have, the it that I plugged in, this type name here. It doesn't depend on whether iterator range itself is const or not. Ugly. Now, let's try a fix. Let's say we have this magic make const iterator, and it's implementable. It's a bit ugly, but it's implementable. We can turn any iterator to a const iterator. Let's say we can do that, okay? And see whether that helps us. Okay, and now we say, okay, if this thing is mutable, then we return it begin. If this thing is mutable, we return it end. But if we return something on the const object here, we will first make the const iterator out of this it begin and it end and return that. Super. Problem solved. No. Someone just circumvented our constness. This is a range. You can make a copy of it because, well, iterator range is copyable. You copy it. Now, this range copy is mutable, and now you can assign to it. And this will assign, since the copy only copied iterators, this will assign to the original range. This stuff didn't help us at all. Oh. Okay, what can we do? Okay, we make range copy. Only copyable. Now, this is basically what people went through when designing a range library. This is what the committee talks about when they are actually, when you are standing there discussing with the people in the C++ conference. It's like, okay, I built this. Does this work? No, this doesn't. Oh, shit. And people kind of discover, bit by bit, they discover the problems. There are going to be more problems. No worries. The range is very peculiar in this case. It starts off with a very simple concept. Something like, hey, this must be so easy. It can't be a big problem. And it turns out that the design of this library is fiendishly difficult. Okay? Okay, now, we said, this is unfortunately still not doing what we want to do. And where's my mouse? I think my mouse is slowly dying. No, actually, we have this one here.
But you have to.
Okay. You make it work, and I keep talking. Oops. Oh hell. Nope. Auto pass array. Excellent. Standing. Okay, constant ranges. Constant range fix one. Fix one doesn't work. Okay. Ha! Now we fix it again. All right? We disallow copying from const objects. Because the problem here is people copied our const object. Okay? This must be disallowed. Can't do that. Okay, so we say we have a copy constructor that only copies references, not const references. This is also a bad idea. Iterator range is no longer a regular type. You can't, for example, things like this, what people expect to work. You have a std vector, that contains iterator ranges, and you want to kind of fill it with 5 times the same iterator range. You always want to fill it with iterator range, it begin, it end, right? Well, this constructor of SID vector takes its type here as const reference, and it expects to be able to copy it. This is one of these basic things that you expect a type to do. This a value type. You create a copy. It's something that should work. And the copy should work from a const reference. So the current consensus is this is not fixable. We have a problem. This is unfortunately, now what is the real problem here? The real problem is we have 2 kinds of constnesses. We have the constness of the thing that we are pointing to, and we have the constness of the thing itself. It's kind of the difference of a pointer to const and a const pointer. These are 2 different things. And for pointers, it's fine because we have 2 places to write a const to. We can write the const in front of the pointer or after the pointer. And that's the difference. Or we can write 2 constnesses in front and after the pointer. And it's all good. Okay? Unfortunately, these ranges we already saw, we have to take by unconstrained template. We don't really know what this thing is. There's no basic type. This is a range, and everyone derives from that type. This is, by design, this is anything that has a begin and end is supposed to be a range. So everyone is right now just kind of saying, it's a problem. We have the same problem actually with iterators, okay? It's the same thing here. If you have an all-off and you have an it begin, it end, you also don't know, is this actually a constant iterator or is that an iterator? It would be nice to be able to say, oh, this is a constant iterator, and then this doesn't work. And so what we really want to do is we want to constrain the template type. We want to say this it should really better be a const iterator in this case. So we want to say, oh, this is a const iterator it, and then this doesn't compile. The only type of, does anyone who hasn't heard of, or who has heard of concepts? Okay, a few of you. There is the attempt to put this into the language, to say you can constrain the templates. You can say this template has to fulfill these kind of requirements if you want to pass it in there. Well, in the best of all worlds, and the full concepts do that, it would also check that the guy taking such a concept only does things that the concept allows. Unfortunately, this has been taken out of the standard. It was close, it was a big discussion, it was close to standardization. They took it out because they had problems. And right now, no one really knows how to implement it right. No one knows how to do it. What they do know are something that's called concepts light. Okay? There, they check all the concepts when this thing is passed into begin. Well, the problem is this will only check the caller. It doesn't check the thing that is actually working on the concept. So, unfortunately, concepts light's not going to help us. Full concepts would help us, but it's nowhere near standardization soon. So, we're a bit stuck. Okay, there's no solution. Range const reference may or may not allow mutating elements. And the range ref may or may not allow mutating elements, because if you're plugging in const iterators into your iterator range, no matter what you're going to do with the iterator range, you're not going to be able to change the elements. So you can't really, either if you're having a range ref or a const ref, you may or may not be able to mutate some elements. Still, the argument passing rules right now are take a range const ref if you don't want to change the elements. Take the range ref if you want to change the elements, or if you want to pass out any strong iterators. This is the rule. Follow it when writing range algorithms, but there's no guarantee. Sorry. We come to exercise number 1. We want this little thing to compile. It's something very simple. You have an array that contains a bunch of numbers, and I want you to write an algorithm. It's going to contain a fair amount of iterators, but it's hopefully going to take a range for each unique range. And it will pass out, it will say, okay, I will divide up this array into ranges that are unique, 3, 3, 4, 5, 6, and then 7, 7. It'll pass this into iterator ranges, make little portions out of that array here, pass them in here, and this, well, I just gave out, like, basically printed the beginning of every one of the ranges. So what you'll get out when you print this thing is 3, 4, 5, 6, 7. Okay? So I would like you to write this thing in the range, in a range style. So for each unique range, should take a range. You can think about whether you need it by reference or refref, or constref or refref. Well, you have to put together an iterator range. I also want you to write the iterator range so that this little piece of code compiles.